Hello all, welcome to the second session of the geometry series. In this episode, we are going to talk about triangles. We're going to cover some basic concepts quickly and then take up some practice questions. So let's get started with the types of triangles. This is something which we all are pretty much aware of, so I'm not going to spend a lot of time on this, but just quickly go through this. So there are three types of triangles essentially: isosceles triangle, equilateral triangle, and scalene triangle. Isosceles triangle is the triangle in which the two opposite sides are of the same length. So in this case, side AB is equal to side AC, and also the two opposite angles, essentially angle ABC, will be equal to angle ACB, right? So that's the first property of the isosceles triangle. The two opposite sides are same and the two opposite angles are also same. Now, when we drop a perpendicular from this vertex A to the base of the isosceles triangle, right, and we drop 90 degree, it bisects this base into two equal parts. So in this case, BM will be equal to MC. Also, this perpendicular will bisect this angle A as well. So angle BAM will also be equal to angle CAM, right? Essentially, each of these smaller triangles, AMB and AMC, are the right angle triangles, and we can use things like Pythagoras theorem or any of the trig functions to each of these triangles. And we will see more of this when we go to the questions. Coming back to the second type of the triangles, it's an equilateral triangle. As we all know, equilateral triangle is the one in which all the three sides are same, all the three angles are same, and hence each of the angles will be 60 degrees because the sum of all the three angles of a triangle is 180 degrees. Just like we saw in the isosceles triangle, when we drop a perpendicular from the vertex to the opposite side, it bisects the opposite side into two equal parts. So BM is equal to MC. It also bisects this angle into two equal angles, right? The third type of triangle is the scalene triangle, in which each of the three sides could have different lengths. Let's talk about the area of the triangle, right? We all know that the area of the triangle is half times the base times height. But the important thing to understand here is that we can select any side of the triangle as the base, and depending upon what side we have chosen as the base, we will have to find the corresponding height, right? Let's see what I mean by that. So let's say we have this triangle ABC, right? Our natural instinct would be to consider BC as the base, which is fine. But how do we find the corresponding height? For finding the corresponding height, we go to the opposite vertex and drop a perpendicular from that vertex to the base, right? And in doing so, sometimes we may have to extend the base. But again, the definition of height would be go to the opposite vertex, drop a perpendicular from that vertex to the base. So for example, if we consider BC as the base, let's say we denote it by B, right, for base. How do we find the height? We go to the opposite vertex, in this case A, and drop a perpendicular from A to the base. So we extend the base and we drop a perpendicular, basically 90 degrees, from this vertex to the base. Let's say it intersects at point T. So AT will be the height of the triangle if we have considered BC as the base. So in that case, the area would be half times base times height, right? Now let's take another case wherein we consider AB as the base. As I said, we can select any side as the base. Now, if we have selected AB as the base, right, how do we find the height? We go to the opposite vertex and we drop a perpendicular from the vertex to the base. So if this is the base, we go to the opposite vertex, which is C in this case, and we drop a perpendicular from C to the base. So we drop a perpendicular or 90 degrees to the base, and in that case, this becomes our height, right? So the area would be given in this case by half times this B times this H, right? We will get the same answer. We will get the same value of the area. It doesn't matter which side we have selected as the base. So this is something which is very important for us to know because it will come into questions as we go along. Okay, so let's try to find the area of an equilateral triangle. Say we have a triangle ABC. It's an equilateral triangle, so each of the sides is same. Let's say each of the sides is equal to S, and we have to find the area of this triangle. We just saw that the area of the triangle is half times base times height, right? So half times base is S times height. Let's say it is H, right? But we don't know the value of H, so we have to find the value of H and plug it in here to find the area of the equilateral triangle, correct? Now, as we discussed earlier, right, when we drop a perpendicular from A to this side, right? It bisects this side into two equal parts. So let's say this side would be, this length would be s by 2, because the total length is s, so each of these sides is s by 2, right? Now when we look at this triangle, let's look at this triangle quickly. So this side is s, this is 90 degrees, a right angle triangle. This side is s over 2, and we have to find this height h, right? We're going to use Pythagoras theorem because it's a right angle triangle. So we can say square of this side plus the square of this side is equal to square of this side. So h square plus the square of this side is equal to square of the hypotenuse, which is s square. So h square plus s square over 4 is equal to s square. We bring it to this side because we are interested in finding the value of h. H square is equal to s square minus s square over 4, which is equal to 3s square over 4, right? We take the square root on both sides and we get the value of h as root 3 over 2s. Because the square root of 4 is 2, the square root of s square is s, and root 3 is like root 3. So we got the value of h in terms of s, which we can plug it in here. So the area becomes half times s times root 3 over 2s, root 3 over 2s, or in other words, root 3 over 4 s square, right? So this is the area of the triangle. So the point I'm trying to make is that if we know any of the sides of the equilateral triangle, we can directly find the area of the equilateral triangle using this ready-made formula, and this is coming right from the Pythagoras theorem. Okay, let's take up some questions now. So suppose we have a triangle ABC such that the length of side BC is 7 and the length of side AD is 10, AD is perpendicular to BC, and the length of CD is 2.35. So we have this situation and we have to find the area of the shaded portion, essentially the area of triangle ABC, right? So there are several ways of doing it, and probably the first reaction which comes to mind is that let's find the area of triangle ABD, because we know the base, we can add these two and find the full base, and we know the height. So we can find the area of triangle ABD. Similarly, we can find the area of triangle ACD because we know this base as well and this height as well, and we can subtract that area of ACD from the bigger triangle to find the area of the shaded portion, right? That's the first reaction which comes to mind when we see something like this. But imagine, right, how much calculations will be involved in doing that, because this has some decimals here. You will have to add 7 to this decimals, get the new base and multiply with 10 to find the area of the bigger triangle, and so on and so forth. But if we look back at our definition of the area of triangle, right, what did we say? We can consider any side as the base and we will have to find the corresponding height. If we look at this question more closely again, right, and if we consider BC as the base, we go to the opposite vertex and drop a perpendicular from the opposite vertex to the base. So this becomes our height if this is the base. So essentially, if we see, we have been given the base and the height both. So this is our base, and when this is the base, the height would be 10. Hence, we don't need to find the area of this smaller triangle. We can directly do half times base, 7 times the height, which is 10, or 7 times 5 is 35. So the area of the triangle ABC would be 35 square units. Okay, let's take another question. So let's say that we have a metal wire in the shape of an equilateral triangle, ABC, right? Each of the sides are same because it's an equilateral triangle. And the area of that shape, the area of that equilateral triangle is 25 root 3. And we're just playing with the wire and we transform that wire into a square shape, right? And we have to find the area of this square shape, right? So essentially, there is one thing which does not change in this whole exercise, which is the length of the wire, because we are not adding a wire or we are not removing the wire. We're just changing the shape from the equilateral triangle shape to the square shape. So essentially, we need to find the perimeter of this triangle. Once we know the perimeter of this triangle, we will know the perimeter of the square. Once we know the perimeter of the square, we can divide that by 4 to find each of the sides, because it's a square, so each side is 1/4 of the perimeter. Once we know the side, we can find the area of the square. So essentially, our problem is to find the perimeter of the, or the length of the wire, right? Now for finding the length, let's say each side is S. Okay, we just saw that the area of the equilateral triangle is given by root 3 over 4 S square. We can directly use that. So root 3 over 4 S square is equal to 25 root 3, because that's the area which is given to us of this shape, right? We can cross multiply and we get root 3 S square is equal to 25 times 4 times root 3, right? We divide by root 3 here, we divide by root 3 here, and we get S square is equal to 25 times 4, which is 100. Or in other words, S is equal to 10, correct? So essentially we are saying that if the area of the equilateral triangle is 25 root 3, each of the sides would be 10. So this is 10, this is 10, and this is 10. Hence the perimeter of the triangle of the wire, the length of the wire would be 10 times 3, which is 30, right? So 30 units. So the perimeter of the triangle is 30 units. Hence the perimeter of the square would also be 30 units. So each of the side of the square would be 30 divided by 4, right? This is the length of each side of the square, right? It comes out to be 7.5. So each side is 7.5 units. Now we can easily find the area of the square, which will be 7.5 times 7.5. So the area would be 7.5 times 7.5, whatever that comes out to be. Okay, let's quickly take another example. So we have a triangle ABC such that side AB is equal to BC, and we have some other angles as given on the board, right? And we have to find the value of angle 3 and angle 4, right? Okay, to start with, right, AB is equal to AC, hence triangle ABC will be an isosceles triangle, correct? And we know that in an isosceles triangle the two opposite angles are also same, hence angle 1 will be equal to angle 2. That's something which we can right away go with. Now this angle here, angle BCD, is 110 degrees. So the remaining angle would be 180 minus 110, which is 70 degrees. So angle 1 is 70 degrees, right? We just discussed angle 2 will be the same as angle 1 because this is an isosceles triangle. Hence angle 2 would also be 70 degrees, right? Now in a triangle, the sum of all the three angles is 180 degrees. Angle 2 is 70, angle 1 is 70. So angle 3 would be 180 minus 70 or 40 degrees. Hence angle 3 would be 40 degrees, right? Quickly talking about angle 4 here. Now we got to look at the triangle BCD. This angle is given as 110 degrees. Angle BD is 140. So this angle would be again 180 minus 140, which is 40 degrees. Now looking at this triangle BCD, this angle is 40 degrees, this angle is 110. The total of these is 150, and the sum of all the three angles has to be 180. Hence angle 4 would be 180 degrees minus 150 degrees, which is equal to 30 degrees. Right. Okay, let's take another example here. So we have a triangle ABC such that angle B is equal to angle C. So that is given, right? The length of side AB is equal to x square. The length of side AC is equal to 2x plus 15, and we have to find the value of x, right? Now when angle B is equal to angle C, it means that this triangle is an isosceles triangle, and hence the two opposite sides would also be equal. Hence side AB will be equal to side AC because the two angles are same. Now side AB is x square and this side is 2x plus 15, so we can actually write x square is equal to 2x plus 15, correct? We can bring everything to the left side and have it like in the standard form of a quadratic equation, and we can try to factor this. We can try to solve this quadratic equation. The two factors would be minus 5 and plus 3. So x square minus 5x plus 3x minus 15 is equal to 0. I'm just using the grouping method. we take x common from these two terms, so I get x minus 5. I take 3 common from these two terms, I get x minus 5 again. And then I take x minus 5 itself common, and I get this, which finally gives me the two values of x as x is equal to 5 and x is equal to negative 3. So these are the two values of x which are possible in this given situation. If x was supposed to be greater than 0, then we would have discarded this value and we would have just kept x equal to 5. So again, basically, right, the trick here is that these two angles are same, and hence it's an isosceles triangle, and hence the two sides are same. Okay, let's go ahead with the last question here. So we have this triangle, bigger triangle ADE, and we have a smaller triangle ABC within the bigger triangle. The lengths are given as shown here. Side AB is 10, BD is also 10, AC is 8, and DE is 12, and BC and DE form a 90 degrees with the vertical line, right? And we have to find the perimeter of this trapezoid BCED, right? So essentially, if we see what we have to find, all we need is the length of side BC and also the length of side CE, because we already know BD is 10 and D is also known as 12, right? So there are two ways of looking at this question, right? One way is that we can simply use Pythagoras theorem in the smaller triangle as well as in the bigger triangle to find the remaining lengths. So let's go ahead with that quickly. So in the smaller triangle, this is 10, this is 8, A, B, C, right? Since it's a 90 degree, we can use Pythagoras theorem. Let's say this is x. So we'll say 8 square plus x square is equal to 10 square. So 64 plus x square is equal to 100, or x square is equal to, you do minus 64 here, you do minus 64, is 36, and x is equal to 6. 6 or minus 6, we discard minus value. So the length of BC is 6, right? Similarly, we use the Pythagoras theorem in the bigger triangle, right? This whole hypotenuse is 10 plus 10, which is 20. This is given as 12, and let's say this is y, and our triangle here is ADE. Again, using the Pythagoras theorem, y square plus 12 square is equal to 20 square. So y square plus 12 square is equal to 20 square. So y square plus 144 is equal to 400. So y square is equal to 400 minus 144, which is 256. Right? We take the square root on both the sides, and we get y is equal to 16. So the length of the overall vertical line AE is 16, out of which AC is already given to be 8. It means that the remaining length would also be 8, right? So you've got all the four lengths of this trapezoid. BC is 6, C is 8, D was already known to be 12, and BD is 10. 6 plus 8 plus 12 plus 10 is 36. So the perimeter of this trapezoid is 36, right? So here in this method we have used Pythagoras theorem both for the smaller triangle as well as for the larger triangle. We can take this question in another way as well. If we really see these two triangles, the smaller triangle and the bigger triangle, are similar, right? They are similar triangles. Now we know that in the similar triangles the ratio of their corresponding sides are same, or essentially the corresponding sides are in the same ratio. What I mean by that is that, so let's say we are saying triangle ABC is similar to triangle ADE, right? So their corresponding sides will be in the same ratio. So AB over AD will be the same as BC over DE, which will be the same as AC over AE, right? Because these two triangles are similar, right? Why they are similar? Because this angle is 90 degrees for both of the triangles, and this angle will also be the same as this angle because they form the corresponding angles, and hence They are similar by A, right? Angle, angle, angle. Now, coming back to this, if we put in the values here, 10 over 20 is equal to BC over DE, right? We can use this to get DE is given as 12, so this is 12 here. So BC will be coming out as 6. Similarly, we can use this one again to find the length of AE, which will come out to be 16. AE is 16, this will be 8. So essentially the point I'm trying to make is that to solve this question, we could either use Pythagoras theorem for both the smaller triangle and the larger triangle, or we could use the similarity of triangles. Hello folks, hopefully you find the video useful and it gave you a good perspective in terms of the triangles, especially some of the rules and properties around the isosceles triangles and equilateral triangles and how we can use them to our advantage. See you in the next session.